Welcome. We're going to start today with Intro to Complex Numbers and solving by using square roots. First thing we're going to talk about is how to estimate where a radical lies between, which two integers it lies between. And that is just by memorizing your perfect squares, both above and below. So that would be 64 and 81. 64 is 8. And 81 is 9. 67 is close to 64. Therefore, the square root of 67 is approximately 8. 134 lies between two perfect squares, 121 and 144. That's 11 and 12. It lies relatively in the middle of, so we're going to say that the square root of 134 is approximately 11.5. 20 lies between 16 and 25. That would be 4 and 5. So that will be roughly 4.5. Remember, it's a negative. 195 between 169 and 196. That will be 13 and 14. That is very close to 196, so we're going to say that it rounds to 14. The radicand is the number inside the radical symbol. Simplifying the following square roots involves finding perfect squares by using prime factorization. All that means is you draw your tree diagrams. 20 will break down into 4 and 5. Is either one of those numbers a perfect square? The answer is yes. That breaks down into 4 and 2 and 2. And your perfect square is removed from the radical because you rewrite it as though it were the square root of 4 times the square root of 5. That's one way to look at it. The square root of 4 is 2, so the answer is 2 square roots of 5. Any perfect square that you can create gets circled, removed from the radical symbol, and all other numbers stay inside. That's 4 and 6. Are either of those two perfect squares? The answer is yes. Again, 4 is. 2 and 2. Now be careful, because 6 will break down. However, 2 and 3 do not have any more pairs along with them, so you can't break it down, so it actually remains 6. So this becomes 2 square roots of 6. Down here, now you're introducing a number outside of the radical. The negative 3 is there. Very simple. Any number that comes out of the radical, that number becomes multiplied by whatever's out there. 9 is your perfect square. That's 3 and 3. Circle it. It comes out. 3 times negative 3 is negative 9. So the answer to this question is negative 9 square roots of 2. Moving on, 30 breaks down into 3 and 10. And 2 and 5. There's nothing that becomes a perfect square, so there is no way to break down 30, so the final answer is in simplest form. 48 breaks down into 6 and 8, or 12 and 4, we can do that. Always look for your perfect squares. 12 and 4 breaks down to 2 and 2. And 12 breaks down into 4 and 3. Always look for those perfect squares. 2 and 2. This time you don't have a single pair of 2's that comes out. You have 2 that will come out. Remember, that is like saying the square root of 4 times the square root of 4 times the square root of 3. Therefore, the square root of 4 is 2. 2 times 2 is 4. And now we multiply 4 times this fraction here, which is 8 over 3 times the square root of 3. It can be very easy for you to forget about the single number that has been prime factored but is still hidden inside of your tree diagram. So please pay particular attention. The square root of x to the 7th power. 1, 2, 3, 4, 5, 6, 7. Circle all perfect squares. There are 3 of them. So that means x to the 3rd power comes out and x remains inside. When it comes to a combination of numbers and variables, it is simple to just break them down each individually. The 12 becomes a 4 and a 3. Remember, look for your perfect squares. That's 2 times 2, so the 2 comes out. Write your total number of x's in a line. Write your total number of y's in the line. And circle your perfect squares. Both x's come out. 1 y comes out, and what's left is 2 times 2, which is 4, x to the 5th power times the square, times the square root of y. When multiplying, it is okay for you to place both radicans under a single radical symbol. So it becomes 3 times the square root of 50. And we can break that back down again into 5 and 10. Breaking down the 10, we get 5 and 2. And there's your perfect square. And it's 15 square roots of 2. Again, place both radicans under the same radical, and we get 4 times negative 3, which is negative 12, times the square root of 6 times 15, which is 90. Break it down. 9 and 10, 3 and 3, there's your perfect square, and 2 and 5. But remember, 2 and 5 is not perfect square, so we can't break it down. I will leave it the way it is. Your pair comes out. 3 times 12 is 36. Square roots of 10. All right, when dividing radicals, you want to be careful about leaving the radical in the denominator. It is not algebraically proper to do so, so we will go ahead and remove that if there is one as we're working. Remember, your calculators will perform the task, so it's not necessary, but it's just not algebraically proper to leave it there. You can rewrite it with both the numerator and the denominator as radicans of their own radical symbols. And since they're both perfect squares, they will both reduce to 5 over 6. Now, before jumping to a conclusion and saying there's a radical in the denominator, rewrite using a single radical and see if it will simplify. If it will simplify, it makes the task a lot more easy before you even begin. 27 divided by 3 is 9. The square root of 9 is 3. In this problem, you'll notice that once we simplify the radicand, you will get a simplified response that will eliminate your denominator. There's your perfect square, comes out in front, so you get 3 times the square root of 3 over 3, and once the number is out of the radical, it reduces or it cancels. All right, rationalizing the denominator is what I was getting at before. That is removing the denominator from, removing a radical from the denominator of a fraction. That process looks like this. Since this is a square root, it takes 2 to get rid of the radical symbol. An example would be the square root of 3 times the square root of 3 equals the square root of 9, which equals 3. Now once we get into other radicals with a different number index, this changes, but the process is still the same. We're using the idea of perfect squares to remove the radical from the denominator of the fraction. Simply put, whatever the number is on the bottom, you multiply it by itself to get rid of the radical. But whatever you do to the bottom, you must also do to the top, and this is the process of rationalizing the denominator. The fraction becomes, exactly like I described to the right, the square root of 3 over 3. Likewise here, we go ahead and multiply by the radical only. We don't need the whole number because the whole number is not the problem, just the square root of 5. Once we do that, we get 4 times the square root of 30 divided by 3 times 5, which is 15. 30 does not break down, as from our prior example. 4 and 15 do not reduce. Your final answer is 4 times the square root of 30 divided by 15. When adding and subtracting radicals, the radicand, that's the number inside, must be identical. In example number 10, they are identical, so you will add the numbers on the outside and leave the radicands the same. 5 minus 7 is negative 2, so the answer to this question is negative 2 square roots of 2. Before proceeding, we must break down 20, 4 and 5. 4 is your perfect square, 2 and 2. The 2's come out. What's left is 3 square root of 5 plus 2 square roots of 5. Now that the radicands are identical, add the numbers outside, leave the radicands the same. 3 plus 2 is 5. 5 square roots of 5 is your answer. Question number 12. We're breaking down a series of numbers and variables. So 16, well, that's easy. 4 and 4. And then we're going to leave the x but break down the y. And we get 4 and y, and we get 4 times 3, which is negative 12, x, y, times the square root of x, minus 2, x, y, times the square root of x. Now that our radicands are identical, we can combine like terms. Notice that xy is the variable on both of the numbers, therefore they are like terms, so the answer is negative 14 xy square root of x. Now, when trying to get rid of a radical that is attached to a plus sign, we must use something called a conjugate. Okay? The conjugate is the whole number and the opposite of the radical. So the conjugate we will use this time is 3 minus the square root of 2. More of this to come in future lessons. 3 minus the square root of 2 is the way that you get these to cancel out. Now the reason for that is the difference of two squares. Once you find that once you recall the difference of two squares removes the center term from this, you'll notice that the radicals are eliminated because one is positive, the other is negative, and they will cancel each other out. So we're going to multiply, and we get 15 minus 5 square roots of 2 divided by a squared, which is 9, and b squared, which is 2. Simplifying the denominator, our final answer is going to be 15 minus 5 square roots of 2 divided by 7. Solving simple radical equations. Please remember, whenever you square root the side of an equation, you always come up with two solutions, the plus or the minus solution. Please keep that in mind as you're solving each one of these equations. First, move the 25 to the other side, and x squared equals 25 square rooted. The answer is x equals plus or minus 5. Add 24 to both sides of the equation. X squared equals 24. Square root both sides. You get plus or minus the square root of 24. However, 24 breaks down because 4 times 6, and 4 is your perfect square. Circle your perfect square, and x equals plus or minus 2 times the square root of 6. Adding 9 to both sides, it's the way that you start number 16. 2x squared equals 9 divided by 2, divide by 2, and now I get x squared equals 9 over 2. Square root both sides, and I can rewrite this using two separate radicals. X equals plus or minus the square root of 9 over the square root of 2. Remember, the square root of 9 is a perfect square, so that's 3, but I'm going to rationalize the denominator because that's algebraically proper, and I get x equals plus or minus 3 times the square root of 2 over 2. Last and not least, add 6 to both sides. 5x squared equals 6, divide by 5, and I get x squared equals 6 over 5. Square root both sides. Remember, two solutions. X equals plus or minus the square root of 6 over 5. Again, not algebraically proper, so I'll go ahead and rationalize that denominator, and I get the square root of 6 over the square root of 5. Multiply both the top and the bottom by the square root of 5, and I get the square root of 30 over 5.